The first thing that I would like to do before I start talking about lecture 8, we have a few things on the agenda. We have response to exponential inputs. We have talked about response of LTI systems for an arbitrary input x of t. We are going to focus today on exponential inputs, and we are going to lay some groundwork for that. Then our second item on the agenda is to represent signals using an orthogonal set of functions. And then that will lead us into one of the core topics of this class, which is Fourier series. Now, before I go into all of these things, we are all fresh, and the first thing that I want you guys to take away from today is this. I'm going to draw, say, a square wave. So a simple square wave. It's periodic with some frequency, some time period, and it is going on, off, on, off, on, off. Right. So it's a square wave signal. Now I want you guys to think about whether you can take a bunch of sinusoids of varying amplitudes and frequency, vary amplitude, vary frequency of these sinusoids, and you can take a bunch of them. You can take, as many as you want. So you can take, really, really small signals in terms of amplitude with a very high frequency. You can change those two parameters of amplitude and frequency the way you see fit. But the goal here is this is a puzzle. So this is like a question that I want you guys to think about while we are going through this lecture and the introduction to Fourier series. So think about taking all these bunch of sinusoids that do not have any sort of a flat nature to them. Take a bunch of them, change their amplitude, change their frequency, add them up, try to get a square wave output by adding up all those sinusoids. Think about that. So one of the things that I was intrigued about when I learned Fourier series the first time was this. I can take a bunch of sinusoids and make them into a square wave by changing their amplitudes and by changing their frequency, and by adding one on top of the other, I will be able to go from those sinusoids which do not have any flat nature to them. They have a smooth up and down, and I can go to a square wave. In fact, I can go to any periodic signal. So that's what intrigued me the most. How can I do this? Can I do this exactly, or maybe I can do this as an approximation? Can I increase my level of approximation, which means that I reduce my error? So all of these topics are sort of what is at play in today's lecture. Those varying sinusoids in terms of amplitudes and frequency, those are going to be called harmonics. So we are going to essentially break up periodic signals into various harmonics, and we are going to find their amplitudes or their coefficients for each harmonic. That's going to be our class today. So to go to this step of being able to do this, there is a lot of underlying math, which is not particularly difficult, but I'm going to take you guys step by step to how we can do this and why this could be helpful. So that's kind of the motivation for today. Let's talk about response to exponential inputs. We have looked at the response of LTI systems to x of t by using the convolution integral. I'm referring to the continuous time signals and systems here. We have looked at the step response of the system. I think that's the last thing that we looked at. Now we are introducing exponential inputs. So the obvious question is, what is so special about exponential signals? In particular, those are complex exponentials we will be looking at. So our first question, importance of complex exponentials. Now it turns out that this complex exponential signal has a very attractive property. And the attractive property here is the response of an LTI system to the complex exponential input is the same complex exponential signal at the output. So if a complex exponential goes in to an LTI system, you get a complex exponential output. The only change happens in the amplitude of that complex exponential. So imagine a complex exponential e raised to st, where small s is the complex variable, also called as the Laplace variable. If you have taken circuits already, you know what a Laplace transform is, you know what the Laplace variable s is. It has some real part and some imaginary part. Sigma plus j omega. S is the complex variable. For those of you who are currently taking circuits, we'll be dealing with Laplace later on in the semester. But right now, I want you guys to treat s, small s, as some complex variable that is related to the frequency, because you see the omega, you know it's related to frequency. So you have this input to this LTI system as e raised to st. T is your time variable. So it goes into this LTI system. Say you have an LTI system with some impulse response h of t, and h of t is provided. Then the output of the LTI system to this particular input is going to be the same complex exponential e raised to st, but there is going to be a change in the amplitude. The amplitude is going to go from 1 to 1 times h of s. So if you had some alpha there, some scalar alpha there, this would be some scalar alpha there, because it's LTI, so it is linear, so it is additive. We know that. But right now, it is the amplitude of the exponential, or the scaling of the exponential on the input side is 1, the output side becomes h of s. So what are you trying to evaluate? You are evaluating capital H of s. What does that denote? That denotes the Laplace transform of the impulse response of the system, which is h of t. And more about the Laplace transform in just a minute. So h of s nonetheless is going to be related to the amplitude of this complex exponential. So whatever function of time goes in, the same function of time comes out. The only change is in its amplitude. Notice that the amplitude is not a function of time. It is a function of s. All right, so you can also consider that e raised to st, which is the function of time, it is a function that is going to be the eigenfunction of this LTI system. And h of s is going to be the amplitudes corresponding to each of those eigenfunctions. So eigenvalue for h of s, eigenfunctions for e to the st. So let us see if this claim is correct. I'm claiming that exponential input goes in, complex exponential goes in, complex exponential comes out, if that is correct. So we'll prove that using the convolution integral. So let's consider an LTI system represented by its impulse response h of t. And we are applying a special input here, which is the complex exponential. X of t is now e to the st. If that is the case, you write the input on the left here. In the middle, you have an LTI system with impulse response h of t. We know that for any input, if I'm given the impulse response, then I can convolve. So to find the output y of t, I can simply convolve the input with the impulse response to get my output. We also know that convolution is commutative, so I can do e to the st convolved with h of t, or write it the other way around, h of t convolved with e to the st. So let's try to expand that into the convolution integral. Y of t is equal to negative infinity to infinity e to the s tau h of t minus tau d tau. That's your convolution integral. Convolution is commutative, so I can write this as negative infinity to infinity h of tau e to the s of t minus tau d tau. So I've just changed those signals around. Now, as you can see, the integration over here is being done with respect to tau. So that means I need to preserve h of tau inside the integral. I also need to preserve e to the negative s tau inside the integral, but I can pull out e to the st out of the integral because it doesn't depend on tau. So when we do that, look at what happens. E to the st is pulled out. You are left with integration negative infinity to infinity h of tau e to the negative s tau d tau. That red box is defined as capital H of S. Why capital H? Because small h is used to denote signals in the time domain, small h. Capital H is used to denote signals in the Laplace domain or the Fourier transform or the frequency domain. So that's how we can differentiate the same signal, one in time domain and the other one in the frequency domain. More about time and frequency domain in the next couple of lectures. And we'll spend a lot of time talking about time versus frequency domains. So that's the definition of capital H of S. This is also referred to as the double-sided. It's double-sided because tau is scanning from negative infinity to infinity. Double-sided Laplace transform of h of t. So if you are given some signal h of t, you can plug it into this integral. You can multiply it with e to the negative s tau, where s is a complex variable, and you can finish up the integral, and that would be the Laplace transform of h of t. So by doing this proof, we have proved that I can write the output of this LTI system as a product of two things. One is h of s, which is essentially my eigenfunction, and h of t, e to the st, which is going to be my eigenfunction. So complex exponential, I can combine that and say one statement that summarizes this proof. Complex exponentials are eigenfunctions of LTI system, and the corresponding eigenvalues are capital H of S. So let's take a look at some examples to see, given an input in the form of a complex exponential, what do you get for the output? So the first one is referring to the one that we just saw, where the input is e to the st. You get e to the st multiplied by h of s as the output. That's the first case. We have already seen that. E to the st goes in, e to the st comes out, but there is a multiplication of h of s. So essentially, you are evaluating the Laplace transform for that particular S. So let's try to answer the two questions that are left on this slide. So the first one is A1 and A2. Assume that A1 and A2 are some values, some scalar values, and actually they could be complex as well. So you can assume that they belong to the set of complex numbers. Now if you have A1 multiplied by e to the s1t, where you can say S1 equals sigma 1 plus j omega 1, and S2 can be defined as sigma 2 plus j omega S2. So, think of it as 5 plus j2, something like that. So you have the addition of these two functions, and each of these functions is a scaled complex exponential going into an LTI system. So this is LTI, and the impulse response of the LTI system is given to us as h of t, and we are trying to find the output. Well, by applying the superposition principle, we can say y of t is going to equal, let's see, I can take a1 e to the s1t and convolve it with h of t, and I also need to add a2 e to the s2t convolved with h of t again. So that's using convolution, I can write the output that way. So that's just using the superposition principle, and I can do that because it's LTI. Now, by using what we learned for complex exponential, I can write A1, the first convolution here. Let me highlight that in yellow. The first convolution here, I can write that as, let's see, A1 remains as is. Now I need H of S1. That's going to be my eigen value, followed by e to the S1t. So that's going to be my first piece, and the second piece is going to be A2 H of S2, let's see, e to the S2t. So, I think it's a little bit helpful if we do an example other than this here. So instead of looking at h of S1 and h of S2, let me add another slide here and try to write this. So suppose you have e to the 2t going in to this system with some signal operator. What comes out? Well, you could say e to the 2t goes in, e to the 2t comes out with h of 2 as the eigenvalue. Similarly, if suppose e to the 5 plus 3j t goes in, what comes out? You get h evaluated at 5 plus 3j multiplied by e to the same function, 5 plus 3jt. So I hope that gives you some a better understanding about what we are talking here. In the examples that we were doing, we were just treating those complex numbers as S1 and S2, but I hope that this is a little bit helpful to put in some numbers to get some clarification. The capital H is a function. We are calling that the double-sided Laplace transform of the impulse response. All right, so coming back, so we got, let's color code this. If this is blue here, then this is blue here at the output, and this is yellow here, corresponding to the yellow shaded one. All right, so that's y of t, that using superposition principle and also the response of LTI systems to complex exponential input. There is a reason why we are doing this. We are continuously talking about complex exponential, and there is a very good reason for this, which relates back to those sinusoids getting added up into a square wave. So bear with me until then. Let's see. All right, so now we can move on to the last one here, where in general, if you say summation, the input is now a summation of a bunch of complex exponentials, and we are using an index I to denote that it is going to be an infinite series going from 1 to infinity, a sub I e to the s sub I t. Those are my inputs. What is going to be the output? Well, you can say here your output is going to be, we can express this as a convolution first. So input is I equals infinity a sub I e to the s sub I t convolved with my impulse response h of t, because this is h of t, this is LTI, all of that. Now, because we know that how our output behaves when the input is complex exponential, you can write this as a summation. I still goes from 1 to infinity. You can leave a sub I as is. You can leave the e to the s I t as is, because that is going to be my eigenfunctions, and their corresponding eigenvalues now will simply get multiplied, h of s sub I. So essentially it's the same example as the second one, but the third one is we are writing it in a more general form. So a few things to note here. The first one is complex exponential goes in, complex exponential goes out. How many, for how many other signals can you say that? It's the same signal going in, same signal comes out of all LTI systems. You wouldn't be able to say that kind of a generic statement for other signals, right? So that's one thing to note about these complex exponentials. Next thing to note is we were able to find out the response or the output of this LTI system to a superposition of all those scaled complex exponentials. We were able to write that in one summation form. All we needed to do was use the same functions, but evaluate the Laplace transform of the impulse response at those specific complex values of S. So S sub I. As soon as we have those become our amplitude scaling, and we can add up all the bunch of complex exponentials, which are still, the eigenfunctions are still a function of time. Now, our next goal is going to be to decompose an input, a periodic input signal, into a summation. So as you can see, if we can break down any periodic input and express it into this form, right, then we know the output for that. Our goal, find the output of any periodic signal. So if I want to find the output of any periodic signal, if I can decompose any input, any periodic input, and express it into a summation similar to this, then I already know its output, right? Because I know for the LTI systems, I already know the output. So that's my next goal. Can we decompose an input periodic signal into a summation like this? Let's do that. We talked about this. All right. So if you want to decompose any time domain signal or any function of time into a summation, then you need to consider an orthogonal set of signals. So essentially, the idea is if you have one signal, you can project it or find its contribution to n different orthogonal signals and add up all those projections to get back your signal that you started off with. Now, orthogonal set of signals, you must have heard the term perpendicular, right? So, the horizontal axis and the vertical axis, the x-axis and y-axis are perpendicular to each other. They are orthogonal to each other. They are mutually independent of each other. Why is that useful? Why is that used at all? It is used because, let me draw a sketch. It is used because you can take, say this is my some x-axis here, some y-axis here. If you have a point, any point over here, you can express that point as, all you would have to do is project it onto the x-axis project it onto the y-axis. Say you have x1 here, x1 and y1, right? As soon as you project your uh, point to those two axes, x and y, you can add up those two vectors to get back your resulting vector x1 comma y1. So all you need to project, because you see what our goal is, to decompose an input into a summation of some complex exponentials. But our goal first is to decompose an input as a summation of signals. And we can decompose an input, over here I'm indicating that as some point, into a summation by projecting it, in this case a two-dimensional space, x and y axis. I project it onto x and y. But in general, if you had an n-dimensional space, then you would take a point, project it onto an n-dimensional space, find out its projection on the first space, second space, third space, and so on each of those spaces, and add those up. And as soon as you add those up, you get back your point in the n-dimensional space. Same thing over here. We are talking about 2 dimensions here. You can expand that to n dimensions. Now, you can expand even further. You can make it more general by saying, I don't have just n dimensions. I have a set of n orthogonal functions. And the claim is that if I take any input, a periodic input, and I project it into to f1 of t, f2 of t, f3 of t, and so on up to fn of t, and add those up, I get back my x of t. So what is an orthogonal set? Let's come back and start talking about the definition of orthogonal set. What is it? A set of functions written up in red over here, f sub 1, f2, f3, so on up to f sub capital N. Those are all a set of orthogonal functions, also called as an orthogonal set, if it obeys this property. The property is, if you find the inner product of fm of t, which is any one of these signals, with another signal from the same set but with a complex conjugate. So this asterisk is indicating complex conjugate. And if you multiply those two signals and integrate over a certain time period, that is the time period for which we are considering that that set is orthogonal. It may not be orthogonal outside of that time, 0 to cap t. So if it is orthogonal, then it has to obey this property. The property is the inner product of those two signals will be 0 when m does not equal n. It will be equal to some finite value E sub m, indicating energy, when m equals n. And this is something very similar to this, right? If you take a vector here, let's see, and you add a vector here, those two are perpendicular, which means that the contribution of one to the other, they are mutually independent. The inner product of the vector pointing in the x and vector pointing in the y direction will be 0. It's the same thing that we are applying over here. The inner product of fm and fn, these signals are belonging to this set. So you can evaluate f1 with f2, f1 with f3, f1 with fn. All those will go to 0 if it is orthogonal. However, if you do f1 with f1, then you get some finite value, e1. f2 with f2, you get finite value e2, and so on. So if a set of signals satisfy this property over some time period 0 to cap t, then they are considered to be orthogonal to each other. So that's an orthogonal set. Now, this could be real signals, these could be complex signals, and there could be several of them. All you have to do is verify whether those set of signals are orthogonal or not. As soon as you validate these with each pair, and you find out whether it is going to 0 or finite value, if it is obeying the property that we have laid out here, you know that they are going to be orthogonal or not. As an example, let us consider a set. We have conveniently chosen a set of complex exponentials. Again, we are going back to that same motivation here. Our motivation is to be able to express an input as a summation of complex exponentials. So to conveniently use this, we are considering an example here where our signals in the orthogonal set are chosen in such a way that you have complex exponentials. So what is this set? You have a bunch of them on this side, e to the negative j 2 omega naught t, e to the negative j omega naught t 1, e to the plus j omega naught t, e to the j 2 omega naught t. So as you can see here, you are considering exponentials at omega naught, plus and minus omega naught, plus and minus 2 omega naught, plus and minus 3 omega naught, plus and minus 4 omega naught, and so on. What are those frequencies? Those frequencies are, omega naught is called the fundamental frequency. Or specifically fundamental radian frequency. You could also say F0 is fundamental frequency, and omega naught as the fundamental radian frequency. How about 2 omega naught? This is the second harmonic. 3 omega naught, third harmonic. What is the time period for which we are considering this to be orthogonal? Cap t, where cap t is 2 pi divided by omega naught. How do you know that? Well, by simply saying omega naught equals 2 pi f0, where f0 is the fundamental frequency, which is also written as 2 pi divided by cap t, which implies that t equals 2 pi divided by omega naught, the fundamental radian frequency. So the claim here is that if you consider a set of signals, set of complex exponential signals, which have some zero frequency component, you see this one, that is just the DC value, that is having no frequency. Then you have plus and minus omega naught, plus and minus 2 omega naught, and so on. The claim here is that that is an orthogonal set of signals with a time period t of 2 pi divided by omega naught. So how can we prove this? Well, we just simply have to prove it using the definition of orthogonality. We said that when m does not equal n, the integration should go to 0. Let's check. We are considering this for time period 0 to cap t, where t again is 2 pi divided by omega naught. We take the first signal fm t to be e to the j m omega naught t. Then we multiply it with fn conjugate of t. So what is that? That is simply e to the jn omega naught t conjugate. So if I write down the definition here, we are doing this for fm fn conjugate of t dt, right? So that we are applying that for our orthogonal set of complex exponentials here. So what is going to happen? The moment you see complex conjugate, that becomes a negative there. So if you can combine these two exponentials, you can combine them into one, e to the j m minus n because you have done a conjugate there. Omega naught t is a common factor between them. dt, you are still integrating from 0 to cap t. This is a simple exponential integration, which should be e to the x divided by, e to the ax divided by a. So you apply your integration identities that you have learned, substitute the limits on that integration, 0 and cap t, where t again is 2 pi divided by omega naught. Omega naught is the fundamental radiant frequency. Substitute the limits, you will see that it evaluates to 0. Now, how did I write that as 0? Now, if you can see this, what is this guy? Let me pull that out here. E to the j m minus n 2 pi. Actually, so let us write this first. What is e to the plus n minus jx? It is simply cosine x plus or minus j sine x. That's your Euler's identity. So I'm using this over here. So I can write e to the j m minus n times 2 pi as cosine m minus n times 2 pi plus j sine m minus n times 2 pi. And as you know, integer multiples of 2 pi for a sine function will evaluate to 0, and integer multiples of 2 pi for a cosine will evaluate to 1. So that should essentially equal 1 because of that. And of course, you have the other piece also as 1, and you get a 0 there. So for m equals n, we have proved that it will be okay, it will be orthogonal. But for m equals n, you need it to be some finite value. Let us check that. 0 to t, e to the j m omega naught t multiplied by the conjugate of the same signal here. Because now this one will be also m, because we are looking at m equals n. So in this case, you have e to the j m minus m, that will be e to the 0, you are integrating over 0 to t, so this will evaluate to a finite value of cap t, which is 2 pi divided by omega naught. That is finite, and we are essentially referring to that as EM, energy in M. So when it was not equal, you got a 0. When it was equal, you got a finite value. Satisfies the condition of orthogonality. Hence, I can claim that the statement I made about this orthogonal set of complex exponentials is in fact orthogonal. All right, let's move on here. After the proof, looked at the Euler's identity. Now let's take a look at how do we break up any periodic input signal x of t into those orthogonal set of functions. What I mean by that is I'm essentially going to look for projecting x of t onto each of those complex exponentials, so that after I project them onto all those complex exponentials, I simply add all those projections to get back my x of t. But in general, it might not be exactly equal, which is why I say it is an approximation. Because if it has to be equal, then it has to be an infinite series. So we can approximate a signal, a periodic signal x of t, using an orthogonal set. So the orthogonal set of functions that we are considering are f1, f2, f3, and so on up to fn. So we are approximating x of t using this orthogonal set, and those functions are defined for that time 0 to cap t. And we do this approximation by evaluating c sub n. C sub n refer to the coefficients. So project x of t onto f1, it will result in some coefficient c1. You remember I said at the beginning of lecture, sinusoid, multiple sinusoids getting added up, their amplitudes, so if you consider adding up like 10 sinusoids, and the first one has the amplitude of 10, the second one has the amplitude of 5, then the coefficient of f1 is 10, coefficient of f2 is 5, and so on. So the coefficients essentially give you how strong are those projections in each of those functions fn. So the claim here is I can approximate x of t as a summation of Cn multiplied by Fn of t. So Fn of t are signals that belong to this set. So this can be expanded into saying this is C1 F1 of t, C plus C2 F2 of t, plus and so on, right? Up to n, Cn Fn of t. So each of these signals here, F1 is here, and so on. So you start off with an orthogonal set of functions. You project x of t onto each one of those functions so that you evaluate C1, C2, C3, and so on. And when you add everything up, it will be an approximation of the signal that you started off with, x of t. Now, what is going to be the error in approximation? Well, it is going to be the difference between what you started off with, which is x of t, and the summation of all your projections, which is that guy right there. In other words, when we were doing that addition of bunch of sinusoids, you may get very, very close to the square wave, but you might not be there absolutely, 100% square wave. So that difference of whatever is left over is the error in approximation. Now, how are you going to choose the coefficients Cn? Can they be arbitrarily large and small? Well, the coefficients should be selected such that the energy in the error signal should be the minimum, right? Should be least. I don't want there to be a lot of error in the approximation. I want that square wave to be as close to square wave as possible. So I am going to select the coefficients, the amplitudes of those sinusoids in such a way that I get as close to the square wave as possible. So coefficient Cn should be chosen based on this logic. Now, a very important, well, I shouldn't say important, a very common question that I get here is this: why minimize the energy in E of t? Why not minimize E of t? So I pose the question to you: why not just minimize E of t? Why are we so concerned about the energy in E of t? Well, that's absolutely right. What would that mean, right? I want to minimize error. So if I say minimize error is, I can go, okay, so if I start with an error of 0.1, if I try to minimize it, if I can go -1, -2, -5, -100, I am minimizing the error. But I'm not really minimizing the energy in the error. So that is the reason why we look at minimizing the energy in the error, and we don't focus on minimizing error, because minimizing error essentially means that you are trying to reduce a number, which in fact means that you are going away from zero error. So when you do the energy, you are essentially squaring things, which is taking care of that deviation away from zero. Not just the absolute value, but the square of the absolute value. Yes. That is why you hear the term MSE, mean squared error. In your other classes, you might have heard the term mean squared error. There is no minimizing error. They try to minimize the mean squared error, which is essentially the same reason here. But we are going to evaluate those Cn, those coefficients, such that the energy in E of t is minimum. All right, let's try to do this. How do we minimize functions of time? Differentiate the function of time with respect to Cn, equate it to 0, and you get the minimum, right? So we are going to use calculus here to give us the minimum of this function, E of t. So let's try to evaluate energy of E of t. We can find out the energy of E of t by, and we are going to call that cap E sub E. This is for energy, this is for error. Next, E sub E. What is that? Integrate over 0 to t. That's the time period over which we are uh, defining the orthogonal set, finding the projections of x of t onto each of those signals. So your integration will be from 0 to t. We are going to square that E of t. So E squared of t dt, that's my energy from the definition of energy of signals. E of t can be written as the difference between the exact representation of x of t and the approximate representation of x of t. Square it, dt remains as is, integration remains as is. You expand that square term, you get 0 to t x squared of t dt, the first term squared, that we are going to define as energy in the signal x of t. That is the exact representation of the signal x of t. So that is E sub x. The second term here is negative 2 times summation of summation remains as is, and summation is with respect to small n. So Cn is inside the integration. You can bring it inside the summation because the integration is with respect to t. Inside the summation, you will have f sub n of t and x of t dt. And the last term over here will be the square of the second term inside that parentheses, which is going to be plus summation remains as is. You have the square of the coefficients Cn squared, and also the integration over fn squared of t. The summation of, so this particular red box, we are defining that as the energy in the nth orthogonal signal. So let me write that down here. This is energy in nth orthogonal function. And this is what? This is the energy in x of t. So once we define those as Ex and En, I can rewrite the energy in the error signal as Ex minus 2 times this summation plus summation of all the squared coefficients multiplied by their energies. Now we want this to be minimum. So differentiate with respect to C sub n and equate to 0. the optimal choice for Cn is going to be the derivative of E sub E, energy of error, with respect to C sub n equated to 0. If you do that, you will get this particular result. C sub n, the coefficients corresponding to each of those orthogonal functions, are going to equal 1 divided by En. That is a scaling 1 divided by E sub n, where E sub n is the energy of the nth orthogonal function. Integration of 0 to t. X of t is the signal that you are trying to approximate or decompose into an orthogonal set of signals, multiplied by Fn. The Fn of t belongs to the set of orthogonal functions. So you see what we did here. We literally did this. We took the signal, we projected it onto F1, F2, F3, F4, and so on, and we've added those up. Right? That's how you get back your signal. And each of the coefficients can be evaluated by finding the projection. So this is essentially finding the projection of x of t on F1 and F2 and F3 and F4 and so on. Right? So I can write this. Finding the projection of x of t on each orthogonal function. No, each signal in the orthogonal set. Right? Because if you have a point in 2 dimensions, you will project it onto x-axis and you will project it onto y-axis, you will get x1 and y1. Those x1 and y1 are essentially C sub n in our case. All right, so that's going to be the optimal choice of the coefficients that go along with each of those functions. Okay. So to go back here, we know this. We know the best choice of Cn. We know that a set of complex exponentials qualifies as an orthogonal set. So we should be able to put these two together and apply it for any x of t. That's exactly what we are going to do here. And because we have proved that the complex exponentials are an orthogonal set, we have the complex exponentials as our f sub n of t in this case. Right now we are using the variable k instead of n. So in this case it's going to be f sub k of t is e to the j k omega naught t, where k goes from negative infinity to infinity. And you are multiplying each of those complex exponentials with a sub k. A sub k is similar to the Cn that we just looked at, the coefficients or the projections for each of those signals in the orthogonal set. So we can actually call this ak as the magnitude of the kth harmonic. It is the magnitude of the kth harmonic, and kth harmonic will be k omega naught, where k is an integer that goes between negative infinity to infinity. So you can express a signal x of t by adding up a bunch of scaled complex exponentials. That is referred to as the exponential Fourier series. Why is it called a Fourier series? Because it's related to the frequency of those complex exponentials. You see the terms are going as, when k is 0, you get the DC value, like there's no frequency there. So that goes to e to the 0, which is 1. But when k is 1, 2, 3, and so on, you get the first harmonic, second harmonic, third harmonic, and so on. first harmonic is the fundamental. So fundamental, second harmonic, third harmonic, and so on. So e to the j 1 omega naught t, 2 omega naught t, 3 omega naught t, and so on. And also on the negative side, omega naught is called the fundamental radian frequency, where omega naught is 2 pi times f0, where f0 is the fundamental frequency. I would recommend that you pick one. I like to work with omega naught. In some textbooks, you might find e to the j k 2 pi f0t. It's the same thing as this. So you can express it in this form or in this form. It doesn't really matter. I like omega naught because it's a little bit more compact. And the time period of this signal x of t is cap t is 2 pi divided by omega naught. I'm saying it is periodic. Is it periodic? You look at those complex exponentials. Can I write those complex exponentials as using Euler's identity? Let's write that. E to the j k omega naught t, right? So let's see that. Where are we writing this? Okay, let's write it here. So e to the j k omega naught t. What is that? Cosine k omega naught t plus and minus j sine k omega naught t. Boom. Right. And omega naught t is 2 pi f0, which is 2 pi divided by t. So you know that these are periodic with a cap t of 2 pi divided by omega naught. Let's come back here. All right. What is periodic? Well, we have when we are talking about classifying signals, we talked about periodic and aperiodic signals. And for periodic signals, the condition is if x of t equals x of t plus some cap t, where cap t is the minimum time period for which this is true, then that is going to be called a periodic signal. And if there is no such cap t that exists, then it will be a periodic signal. Note, cap t is the minimum time period. You can obviously go 2 times that, 3 times that, and you will get, it will also be periodic at those times. But cap t is the minimum time period for which this is true. All right. So our goal, what is left here? If we want to express any periodic signal x of t as a summation of complex exponentials, which goes back to the same motivation here. If you know how to decompose an input as a summation of complex exponentials, then we already know the output of those signals, because those outputs are those exact same exponentials with a change in the amplitude. The eigenvalues change, that's it. Eigenfunctions don't. So all we need to find in this one is a sub k. And as soon as you find a sub k, the coefficients, the Fourier series coefficients, we are done. We can express any periodic signal as a summation of complex exponentials in this case. And we know the output of LTI systems to those inputs. Okay, so to help with some simplification, I have sketched one time period of a cosine over here, which relates to the Euler's identity. E to the plus or minus j omega naught t can be written as cosine omega naught t plus or minus j sine omega naught t. Now, if you integrate over one time period cap t, what are you going to get? Integrate over one time period, e to the plus or minus j omega naught t dt can be written as two integrals over here. First for the cosine plus or minus j and the sine. When you integrate over one time period for cosine, you can see that the green area will cancel out with the red area over here. The positive area will equal the negative area as long as you integrate over one time period. If you go a little bit more or a little bit less than one time period, then you will have a non-zero result. But because we are considering this to be for one time period, you are going to have an area of 0 for cosine. And similarly, when you sketch this for the sine, the positive will cancel out with the negative. You can quickly do that. All of this will cancel out with all of that for one time period. So even this guy will go to 0. So what we are writing, we are going to use this later during a simplification step. But essentially what we are saying is, if we take e to the plus or minus j omega naught and integrate it over one time period, you will get a 0. So while we note this, let us move on. Because our final goal is to just find the Fourier series coefficients, we are using a sub k to denote the Fourier series coefficients. Our goal is to find those AKs for a given x of t. And if we are able to do that, we are done with Fourier series coefficients. And in that attempt, let us start with a sub 2. A sub 2 is the magnitude of the second harmonic component of x of t. So if x of t can be broken down into multiple harmonics, one with frequency 0, one with frequency omega naught, one with frequency 2 omega naught, one with frequency 3 omega naught, and so on, a sub 2 is the magnitude of the second harmonic, which is corresponding to 2 times omega naught. So let us try to find a2, and it will give us hints about how to find a sub k. So we are going to play a few tricks over here just so that our math becomes easier. So in order to find a sub 2, what we are, let us try to multiply x of t by e to the minus j 2 omega naught t. I have conveniently chosen 2 omega naught t because I am after a sub 2. Now, what does that multiplication mean? Let's see. From earlier, the definition of actually, you know what? Let's see. Let's do this. Consider this equation here. Copy it and paste it over here. We reduce it in size. All right, let me have that as reference. So essentially what I'm trying to do here is I am trying to multiply x of t by e to the negative j 2 omega naught t. So essentially I'm multiplying the left hand side as well as the right hand side of the Fourier series definition here. So when I do that, I have on the left hand side x of t multiplied by e to the negative j 2 omega naught t. On the right hand side, I can put that negative 2 inside that summation as well as inside that power of the exponent, e to the j k minus 2 times omega naught t. So I've got k from here and 2 from here. So k minus 2. All right. So once I do that, I'm going to integrate over one time period. And there's a reason why I'm integrating over one time period, cap t, because I said that signals coefficients can be evaluated by integrating over one time period. So let's see, let's go back here, integrate over one time period. Left hand side is x of t e to the minus j 2 omega naught t equals, summation sign remains as is, ak can be outside the integral because the integral is with respect to time. So the integration can be over one time period, e to the negative, j k minus 2 omega naught t dt. So essentially I'm integrating both left and right hand side of this equation here. Next, I'm going to write each element in this summation. As k is an integer going from negative infinity to infinity, I can break up this summation into multiple terms. So for example, you will have a bunch of terms over here corresponding to a sub minus 2, a sub minus 3, a sub minus 4, and so on. But if I look at k as -1 over here, I get the first term. Not the first term, I get this term. That is when k is -1. And this guy is k equals 0. And then I can also write one more term, maybe let us see this one. This one is for k equals 1. Now if you have, so basically we have broken up into a1 or a sub 1 integrate over one time period e to the j times k is -1, so -1 minus 2 omega naught t remains as is, and we have written that up into a summation. We are basically writing out each term in the summation. So what do you think this is going to be? What do you think? Let's see. The first term highlighted in blue is going to be. Use this integration over one time period e to the plus or minus j omega naught t dt is 0. So even if you have multiplied by k, or maybe I should write some other one. Let me use multiplied by some m, where m is an integer. What do you have? You will have m omega naught t here, m omega naught t here. What will that be? It will still be 0. So the first term, can I say that that equals 0? Because it is e to the negative 3 j omega naught t. How about the next guy? Also 0. Why? Because you have e to the negative j2 omega naught t. How about the next one? Also 0. Because you have e to the j negative j omega naught t. They are all 0 except for this guy. Because over there, what do you have? A2 times integration over one time period e to the j times 0. So that goes to a 1, which means integration of 1 for one time period will result in simply cap t. So you see what happened here. Maybe I use this. Integration of x of t multiplied by e to the negative j 2 omega naught t equals a2 multiplied by t. Everything else is 0. So we can write this. So essentially everything went to 0 here, everything went to 0 over there. The only term that was non-zero was a2 times t, which means I can write a2t equals integration over one time period x of t e to the negative j 2 omega naught t dt. Notice 2, 2. Simplify a little bit. A2, the magnitude of the second harmonic is 1 over t integration over one time period x of t e to the negative j 2 omega naught t dt, where omega naught is 2 pi over cap t. Now, if you apply the same procedure to find the exponential Fourier series coefficients a sub k, what is going to happen? Ak will become k there, right? So Ak, those are the magnitudes of the kth harmonic component, will be 1 over t integration over one time period x of t multiplied by e to the negative j k omega naught t dt. project the signal x of t onto each of those orthogonal set of functions, and when you do that you will get their corresponding magnitudes. That's the magnitude of the kth harmonic component. And once you find those components, you're done. You're basically broken up that periodic signal into a summation of complex exponentials, and you know their magnitudes by evaluating a sub k. And if you do that, you know the output of the LTI systems to those inputs. All right, so the numerical problems that will be related to Fourier series will more or less focus on evaluating a sub k's. A couple of things that I want to mention over here. One is, when you look at this integration of one time period, this is a choice. This is up to you, because there is one time period. What I mean by that is this. Let's see. Well, I will talk about that in the context of the example that we are just going to do. When I say integrate over one time period, somebody could choose 0 to 4 in this case, right? 0 to 1, 4 is one time period for this x of t. Somebody else could come in and say, I will choose from -1 to 3. That is also one time period. And some other person will come in and say, I will choose from -2 to 2. That is also a time period. In fact, there are infinite time periods that you could choose from. -1.1 to 2.9 is also a time period. So the point is, the limits of the integration should be chosen such that your math is easier. The thing to note is, no matter what integration limits you choose, you will get technically the same answer if you do your math right. However, one approach might be frustratingly difficult, and one approach might be very, very simple. One quick trick is, when you have an even signal like the one that is shown over here, it is symmetric about the y-axis, then you try to choose the integration limits that correspond to one time period as -2 to 2, also in a symmetric manner. That will help you simplify things much easier. So don't use the yellow, don't use the blue, use the pink is what I'm suggesting. And you will see this when we are doing this example. You will see how this can be very useful. Next, that's one thing I want to talk about regarding the choice of the time period, which will essentially set the limits of the integration. The second thing that I would like to emphasize on is, find a sub 0 first. A sub 0 is the average value of the signal, is related to that, and I'll prove it in just a bit. But the reason why I am saying evaluate a sub 0 first is because when you evaluate a sub k, sometimes 0 might not be included in the general answer, the general form. So when you substitute 0, sometimes what happens is you will get an undefined form, 0 divided by 0. So try to find the coefficient a sub 0 first, which is the DC component, which is the average value in the signal x of t, and then try to find out a sub k where k is not equal to 0, the general answer. So try to break it up into 2 steps. First find a sub 0, then find a sub k where k is not equal to 0. Sometimes you might see that everything is included, even k equals 0 is included in a sub k, the general form, and sometimes it cannot be included because you will have a 0 divided by 0 situation. So be aware of that possibility, and you can navigate around that problem by trying to find out a sub 0 first separately from a sub k. All right, so let's try to move on here and focus on the first example of Fourier series coefficients. Here we have a square wave signal. We are asked to find and sketch the Fourier series coefficients a sub k for the periodic signal x of t. So I'm going to denote x of t, and this is a rectangular square wave that is going on both negative and positive sides. It is 1 between negative 1 and 1, 3 and 5, and so on. It is even. And I'm denoting x of t followed by an arrow that is pointing in both directions, Fs standing for Fourier series, and the Fourier series coefficients are denoted as a sub k. Why is this a double arrow? It is because given x of t, you can find out a sub k, and given a sub k, that will correspond to that x of t. So it goes both ways. All right. So what do you need? Well, I need a sub k. How can I find a sub k? As I hinted before, find a sub 0 first. Before even you find out a sub 0, which is the second here, find time period of the periodic signal first. Time period of x of t, as you can see here, time period can be from negative 1 to 3 or 0 to 4 or 1 to 5. Whatever you pick, time period will be 4. If time period is 4, the fundamental radiant frequency omega naught will be pi over 2. 2 pi divided by t. The average value of the signal, what do you think it's going to be? Somewhere around here, right? Can you guys guess? Well, it is written, but even without doing the math, could you have guessed half? Yes, absolutely right. Half the time it is on, half the time it is off. So if it was on all the time, it would be 1. If it was off all the time, it would be 0. If it is on half the time, half of the time. So the average value should be exactly half. Yes. So even without doing all this math, you could have done it, but we have that math over here that supports our reasoning. So let's take a look at the math. Average value of the signal, a sub 0, also called as the DC component. 1 over t, integrate over one time period. What time period are we choosing here? Let us see. The time period that I recommended was this. Negative 2 to 2. That's my time period. So 1 over t, that is 1 over 4. Integration from negative 1 to 1. Oh, right. So because negative 2 to negative 1 is 0, 1 to 2 is also 0. So you are essentially evaluating only from negative 1 to 1. And during that time, x of t is 1 dt. So you evaluate that a sub 0 to be half. Now that you are done with a sub 0, you move on to a sub k in the general form. We'll do it over here. Now we find the other exponential Fourier series coefficients, a sub k when k is not equal to 0. In general, you can say a sub k equals 1 over t integration over one time period x of t e to the negative j k omega naught t dt. Where did we see this before? We saw this right here. We derived it. We started with the second harmonic component a sub 2 and then we generalized it to a sub k. Ryan asked a question in the chat box saying if x of t was not 0 at negative 2 to 2, would you integrate from negative 2 to 2? Yes, I should say I started off with -2 to 2 and then I changed that to -1 to 1 because other times it was 0. Let's see. There is a note that I make on the bottom of this slide, which is what I hinted to earlier, which is if you have a period t that you choose from -2 to 2, then it will help you simplify things a lot easier. It will make your math a lot easier to handle. In general, if x of t is even, like it is over here, then choose the time period as -t/2 to t/2, also in an even manner, where cap t is the time period. So this note comes in very, very handy when you're dealing with the math related to finding a sub k. And you will see this over here. So we start off with the Fourier series coefficients, the formula for that. Plug in the values for t, omega naught. You get what? 1 over 4, -2 to 2, x of t, e to the negative j k omega naught t. X of t is 1 from -1 to 1. So you have changed the limits here of integration, and x of t was 1, so it's simplified to e to the, just integrating e to the negative j k omega naught t, which is e to the j k pi over 2 t divided by negative j k pi over 2. 1 over 4 remains as is. So 1 over 4, 1 over 4. I think you guys see where this is going. T is 1 over 4, which means, oh sorry, t is 4, which implies omega naught is pi over 2, and which is why we are using it here and here. All right, next we are going to simplify things a little bit. So you have 1 over 4, which continues to be there. The factor here, negative j k pi over 2, can be pulled out. And then what, after you substitute for small t as 1 and -1, you will get e to the negative j k pi over 2 times 1 minus e to the negative j k pi over 2 times -1. So what is that? What is this guy? Sine x is e to the jx minus e to the minus jx divided by 2j. So what is that going to equal? There is going to be a minus up front, and there is going to be a 2j multiplying factor, and sine k pi over 2. Next, the negative sign will cancel out with that negative sign. The 2 in the numerator will make this guy 2 in the denominator. J in the numerator will cancel out with j in the denominator. So what your result is half sine k pi over 2 divided by k pi over 2. Let me erase those things so that it doesn't confuse you later on. Half times sine k pi over 2 divided by k pi over 2 when k is not equal to 0. Now I hope at this point you see why we are stressing out about 0 and k not equal to 0. If you plug in k equals 0 here, it will be 0 divided by 0 form, and you will have to use L'Hopital rule, which is why we calculated a sub 0 separately and first. All right. Sine x divided by x, what is that? Half times sinc x. So Max asked a question, sine x identity, should we know that? Max, when you reviewed complex numbers, the answer is yes, you should know that. Let me write down a few notes over here so that we have it formally. Cosine x equals e to the x. Wait a second. Yeah. And then sine x. Yes, it follows the Euler's formula. Yes. All right, let's move on here. So the final answer over here is half times sinc k pi over 2. Now, whenever I think of a sinc function, let me talk about the sinc function later. You will see the sinc function being used several times over the course of next few weeks. So it's good to see it graphically. It is good to know its definition, and it is also very important to know the two most common forms of sinc function. This is, by the way, when k is not equal to 0, because when k was equal to 0, a sub 0 was half. We already found that out. All right. So an important note about sinc function. It looks like this. So it is sinc sine x over x in general. In our class, we will be using sinc of x as sine x over x. However, there is another very commonly used form which MATLAB also uses, which is sine pi x divided by pi x. And some other textbooks also follows this. So don't get confused about the different forms here. The shape, as you can see, looks the same. On the left, I am sketching a sinc function. X-axis is x, and I'm sketching the sinc function as sine x over x. On the right, I'm sketching the same sinc function, but here the definition is sine pi x divided by pi x. And the x-axis is also x. So it is good to know how they differ. Their peak is at time when x is 0, you have a peak, and after that it ripples down. By the way, whenever I think about a sinc function, I imagine like somebody throwing a stone into a pond. When somebody throws a stone into a pond, what is going to happen after a moment or two? There is going to be the water is going to rise up, and there are going to be ripples. So that is what I imagine when I that is what I picture when I picture the sinc function. Those are all the ripples that are going away from the place the stone landed in. Wherever the stone landed, you will have that water come up from above the surface. So what is the difference graphically? The difference literally is the places at which the sinc function crosses 0. So for sine x divided by x, let me write this in blue, the sinc function crosses 0 when it is pi, 2 pi, 3 pi, and so on. Over here you have negative pi. Over here you have negative 2 pi, and so on. So integer multiples of pi other than 0, those will be the zero crossings of the sinc function when you sketch it as sin x over x. When you do sin pi x over pi x, the zero crossings will be at 1, 2, 3, and so on. So that's the only difference between those two forms of sinc function. In our class, as I said, we will be using sin x over x. So I will push for that. So that's how we can view this sinc, half sinc k pi over 2 now. All right, so what we'll do is we'll try to consider the first 6 harmonic components in our example. I'm sketching k equals 0, 1, 2, 3, 4, 5, 6. I have evaluated a sub k. I have plugged in k as 0, 1, 2, 3, 4, 5, 6. I see that the even harmonics are equal to 0. When k equals 0, we got the average value, the DC value. And when k equals 1, it is 1 over pi. When k equals 3, it is negative 1 over 3 pi, and so on. So if I take a look at a sketch here, let's come back to this later. If I take a look at a sketch here of the first 6 Fourier series coefficients, on my x-axis I have k, on my y-axis I have a sub k. How are those coefficients going? At 0, I have half. At 1 and minus 1, I have 1 over pi from the table before. 2 and negative 2 evaluated to zeros. 4 and negative 4 evaluated to zeros, and so on. So the overall shape is a sinc envelope. So essentially, this is like we are sampling a sinc function. Those are our first 6 harmonics. So we have 0, plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 4, plus and minus 5, up to the 5th harmonic. We have sketched that to relate the coefficients to an overall sinc shape. So I want you to see a relationship between the time domain signal that we started off with and the Fourier series coefficients envelope. We started off with a square wave, a rectangular pulse, and we ended up with a sinc. Rectangle and sinc. These two terms should go hand in hand for you now. Now, we have, before I end this lecture, I want to tie up one thing that I started off with. How do you go to that square wave? When you sum up all those sinusoids. So as you are summing up multiple sinusoids, or on this particular graph that I generated using Fourier series coefficients in MATLAB, the blue line is x of t, the rectangle, the periodic square wave, and the red one is the approximation of x of t using the Fourier series coefficients. So the code is over here at the bottom, and you can refer to it later on, and we'll revisit this when we come back on Monday. But to close the loop on that question that I asked, it is essentially adding up all these sinusoids. As you can see, the red one is the DC value, the average value. Then there is a fundamental, which means that it is the 1 omega naught, which is doing this, the yellow one. Slow frequency, but a higher amplitude. That is, the amplitude is essentially your A1 and A minus 1. Then you have the third harmonic, the blue dashed line. And then you have the fifth harmonic, because we already said the even harmonics are 0. So when you add up all those pieces, DC, fundamental, third harmonic, fifth harmonic, you get this red line here. And as you can see, it is tending closer and closer to the square wave. And if you do more and more, what you will see is this. So it will tend towards a square wave as you sum up more and more harmonics. This is essentially the first 6 harmonics, which is why this is a pretty good approximation, but it is still an approximation. But if you look at 10 harmonics, 20 harmonics, 100 harmonics, it'll go closer and closer to the square wave. And that's how we go from adding up bunch of sinusoids to get a square wave. All right, let us stop here. I did not complete the example of the square wave periodic signal. I will revisit it when we come back on Monday.